In this video, we want to talk about the extreme value theorem. And so this is kind of a continuation of the idea of maximums and minimums. So the extreme value theorem says the following. If f is continuous on a closed interval a to b, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some points c and d in the interval a to b. So what this is telling us is if we have a function that's continuous on a closed interval, it will have a maximum and it will have a minimum, meaning an absolute maximum and absolute minimum. And so just graphically what this is saying, if we've got some closed interval, there is going to be a largest point. So this would be our point C, this would be our point D. There will be a largest point and there will be a smallest point if we're on a closed interval with a continuous function. Now, if the function is not continuous, then we don't have to have this satisfied. So if f of x is not continuous on a closed interval a to b, this may not be true. And so, for instance, we could have the following setup, where we have this function right here, and this function does not have an absolute maximum, because we have a hole where its absolute maximum would have occurred. But this function is not continuous on the interval from a to b, and so because of that, the extreme value theorem does not apply. But notice this graph does have a minimum. And so there is a minimum value. The minimum value is right around here, and it's 0. And so there is an absolute minimum, even though there's no absolute maximum. So you may get absolute minimums and maximums, but you may not if the function's not continuous. But you're guaranteed to get them if it is continuous. And so what we want to do is we want to figure out a way of actually computing these absolute maximums and minimums that we know are guaranteed. And so what we use is what's called the closed interval method. So now the closed interval method is just a way to find the absolute maximum and minimum. And so this is steps to find the absolute max / min of a continuous function f on a closed interval a to b. Okay, we are guaranteed by the extreme value theorem that they exist, and this is just telling us how do we find them. So let's talk about what the closed interval method says. So step 1 is find all the critical points, or critical numbers. So again, these are places where the derivative either is 0 or does not exist, but the point is in the domain. So these would be points in the interval a to b where the derivative is 0 or does not exist. Step 2 is find the value of f at each of the critical numbers So you're just going to find the value of f at all the critical numbers, so you literally plug the critical numbers into the function f. Step 3 is find the values f of a and f of b. So you plug in the two endpoints, find the values of the function at those endpoints. And then step 4 is literally just reading off your answer. And so the absolute maximum is the largest value found in steps 2 and 3. The absolute minimum is the smallest value found in steps 2 and 3. So you just take all the numbers from steps 2 and 3, which are the values of the function at its critical numbers and at its endpoints. The largest of all those is the maximum. The smallest of all of those is the minimum. So let's do some examples of using this closed interval method. And so the first example we're going to look at is the following. So we want to find the absolute max and min of f of x equals x cubed minus, it's x cubed minus 3x squared plus 1 on the interval -1/2 to 4. Okay, so this is a polynomial, so it is continuous on -1/2 to 4. So we're just going to take the derivative and find the critical numbers to start with. And so that's step 1. So step 1, we're going to take the derivative and find the critical numbers. So we get 3x squared minus 6x plus 0. So this is 3x times x minus 2. And so this will be 0 when x equals 0 or x equals 2. So our critical numbers are x equals 0 and x equals 2. And so we know those are the only ones because f prime is a polynomial, so it's defined everywhere. So we only needed to know when it was 0. Now, for step 2, we're going to plug these values into the function. So we plug them into the original. So we want f of 0 and f of 2. Well, for f of 0, we get 0 cubed minus 3 times 0 squared plus 1. So we get out 1, and at 2, we have 2 cubed minus 3 times 2 squared plus 1, which, plugging those in, we get out a value of 8 minus 12 plus 1. So we get minus 3. Okay, so that's f of 0 and f of 2, which is step 2. For step 3, we're going to plug in the endpoints. So we want f of -1/2 and f of 4. So I'm just going to give you the values here. So if you plug in -1/2, you get out 1/8. And if you plug in 4, you get out 17. So now step 4 is just identifying things. And so we have the absolute max. The absolute max is where the largest value occurs. Our numbers are 1, -3, 1/8, and 17. 17 is the largest, so the absolute max is the point 4, 17. Remember, the value is 17, and it occurs at 4. The next, we want the absolute min. And so here we just take the smallest value, which is -3. So this occurs at 2, -3. And so the absolute minimum value is -3. And so that's just how the closed interval method works. So find the critical numbers, plug in all the critical numbers and the endpoints, then just pick out your answer. So let's look at another example of doing this. And so next we're going to take the following function. So f of x is going to be x minus 2 sine of x. Okay, so once again, this is defined for all real numbers, and we're going to look at the interval 0 to 2 pi. So a function is x minus 2 sine of x. we want the absolute maximums and minimums on 0 to 2 pi. So I'll write that down. So we want to find the absolute max and absolute min. And so step 1 is to take the derivative of this function. So the derivative is going to be 1 minus 2 cosine of x. So we have 1 minus 2 cosine of x. Now we need to know when this is 0. It always exists, so we just care about when it's 0. So we want 1 minus 2 cosine of x equal to 0. So 1 equals 2 cosine of x. And so cosine of x equals 1/2. So we want to know the values where cosine of x equals 1/2. And we only care about the interval 0 to 2 pi. And so this occurs at, if we just use the unit circle, this is at pi thirds and 5 pi thirds. Okay, so pi thirds and 5 pi thirds are our critical numbers. So these are our critical numbers. Now that we have our critical numbers, we want to plug those into our function. So we want f of pi thirds and f of 5 pi thirds. So at pi thirds, we're going to have pi over 3 minus 2 sine of pi over 3. And this equals pi thirds minus the square root of 3. And that's approximately negative 0.684. At 5 pi thirds, we have 5 pi thirds minus 2 sine of 5 pi thirds, which equals 5 pi thirds, and then plus the square root of 3. So sine of 5 pi thirds is negative square root of 3 over 2, so we get plus square root of 3. And that's approximately 6.968. So those are the values at the critical numbers. Now we need the endpoints, which are 0 and 2 pi. So we want to plug in 0 and plug in 2 pi. Plugging in 0, we get 0 minus 2 sine of 0. Sine of 0 is 0, so this is just 0. Here we get 2 pi minus 2 sine of 2 pi. Sine of 2 pi is 0, so this is just 2 pi, which is approximately 6.28. So now we've found all of our values at critical numbers and all of our values at the endpoints. So we're just going to read off our answer. So we have our absolute max and our absolute min. And so the largest value showing up of these four, I'll underline the four values. The largest value is 6.968. So we have 5 pi thirds, comma, 5 pi thirds plus square root of 3 is our absolute maximum. And the smallest of all of them is negative 6.84. And so that is going to be our minimum. And so pi thirds, comma, pi thirds minus the square root of 3 is our absolute minimum. And so we were able to find both our absolute maximum and absolute minimum for this function. So now let's look at one more example. So this is a type of question that you might actually see in the real world. You might want to solve such a problem. And so we have a particle has a position function given by s of t equals 4t cubed minus 6t squared plus 10t minus 3 on the interval 0 is less than or equal to t is less than or equal to 2. And so we've got this situation of some particle. We know its position function and we care about it on the time interval from 0 to 2. We want to find the absolute maximum and minimum values of the velocity of the particle. So we want to figure out the place where it's moving the fastest in the positive direction and moving the slowest in the negative direction, or the absolute maximum and minimum. Now we want this for the velocity, meaning that the velocity function is the thing we want the max and min of, not the position function. So we need to find the velocity function to start with. So the velocity function, recall, is the derivative of position. And so we're going to take the derivative of our position function, which is 4t cubed minus 6t squared plus 10t minus 3. Taking its derivative, we get 12t squared minus 12t plus 10. And so that is our velocity function. But we want the maximum and minimum of the velocity function. And so now we're going to use the closed interval method on v of t. So we're going to use v of t to find the absolute maximum and minimum. So we're going to use the closed interval method. So we take the derivative. Its derivative is going to be 24t minus 12, which equals 12 times 2t minus 1. And we want to know when this is 0. So this is a polynomial, so it always exists. So this is going to be 0 when, well, let's just set equal to 0. So 0 equals 12 times 2t minus 1. So 0 equals 2t minus 1. 2t equals 1. And so t must be 1/2. So 1/2 is our only critical number. And now we're going to plug things in. So we've got our critical number, so we're going to plug it in to our velocity function. So we plug 1/2 into v of t. This is going to be 12 times 1/2 squared minus 12 times 1/2 plus 10. This becomes then 12 over 4 minus 12 over 2 plus 10, which is going to be equal to 3 minus 6 plus 10, which is 7. So at 1/2, we are at 7. Now we need to plug in our endpoints of 0 and 2. Plugging in 0, we're going to get 12 times 0 squared minus 12 times 0 plus 10, which is 10. Plugging 2 in, we get 12 times 2 squared minus 12 times 2 plus 10. And this becomes 34 if you simplify it. And so we get those values. And so the absolute max and absolute min we can just read out of the problem. And so the absolute max velocity, well, it's going to be the largest of those values. We had 7, 10, and 34. And so 34 is the largest, so it's going to be at the time 2, comma, it's going to be when t equals 2, and the velocity is equal to 34 at that place. Then we want the absolute min velocity. Well, this is the smallest of those values, which is 7. And so that's going to be when t equals 1/2. And the velocity there is 7. So we're able to find the absolute max and min velocity doing this procedure. Now, one thing to note is that we did not have two critical numbers here. We only had one, but we still have an absolute max and absolute min. And that's because absolute max and absolute min can occur at endpoints, which is why we have to check the endpoints to begin with.